Hello everyone, welcome to Abstrak. On this occasion, we would like to provide a tutorial on how you can use AbstractDAMSMEL for an optimization problem. So in this project, we would like to create a mathematical model for Indonesia historical carbon emission based on a dataset provided by Gutschow and Pfluger, which you can access on the Zenodo repository. First of all, we are very grateful with the availability of this data and to the authors. And for your information, this dataset is openly available under the CC BY 4.0 license, which means that you can use this dataset as long as you provide proper credits to the authors. We will include the link to the Zenode repository on the description. So let us get back to our notebook. First of all, we need to install AbstractDAMSMEL package from our GitHub repository, which we have done. For you who have not understand on how you could install AbstractDAMSMEL, please visit our previous video on the installation of AbstractDAMSMEL. Okay, now we need to import the necessary libraries for this project. These libraries include NumPy and then pandas, and we will need to visualize some stuffs in the process. So we would import pyplot from matplotlib, and perhaps cpon 2, and also we need to import a DAMSMEL Python class. You can also do that by copy the code from AbstractDAMSMEL repository here to your notebook. Okay, all set. Now let's run the cell. Okay, we have successfully imported all the necessary Python libraries. To check that we have properly imported AbstractDAMSMEL package, here we can run the code help DAMSMEL. Here we can see the documentation of DAMSMEL, meaning that we have successfully imported DAMSMEL in this notebook. Okay, now we need to import our dataset. For your information, the dataset we use here have been pre-processed earlier, and we claim that we did not do any modification to the original dataset. We only filter the necessary information of the dataset for our project, which is Indonesia historical carbon emission. So now we import the dataset, which is in CSV on our Google Drive. You can also download the dataset from the Zenodo repository and store on your own storage, and you can use the dataset as long as you put the proper credits to the authors. Now let us observe the first 10 rows of the dataset. And also the last 10 rows of the dataset. And for a better intuitive understanding on the dataset, we can visualize the dataset. Okay, I would like to change the color to blue, the trend line color. So here we have the plot of Indonesia historical carbon emission from approximately 1750 to 2022. If we observe this graph thoroughly, we would guess that it resembles an exponential function. To confirm this hypothesis, we would plot such an exponential function. So let's generate an exponential function dataset. Like to only use the number from 0 to 100 as the input or index. Then the function may be denoted by f. Okay, here we can see the plots, and as we compare, we get that they take almost similar shape. It implies that we can use the exponential function to model our dataset. Okay, before we proceed with more detailed modeling of the dataset, we would like to normalize the values in the dataset for a very accurate solution provided by DAMSMEL. So we would use min-max scalar, which we would create ourselves here. We will also need an inverse of this normalization, so we create a new Python function called inf-min-max, which would serve as the inverse min-max normalization. It should take two arrays. The first is norm array, which indicates the already normalized array, and the other array is the ORI array, which should be the original array. Vmin, the minimum value, this is the minimum value of the original array. Then Vmax is the maximum value of the original array. And then here we recreate it as the inverse min-max of the array, which can be done as follows. Okay, norm array, return recreate it. Run this cell. Now we do normalization to our dataset. So we will create a new dataset. We would say df norm first. We now normalize the year. It can be done as follows. And then we normalize the Indonesia carbon emission. Okay, so here the new normalized dataset. Perhaps we also want to plot this normalized dataset. So this is the new normalized dataset. You can notice here that the maximum values of either the x-axis and the y-axis is 1. Okay, so now we proceed with the modeling of the dataset. We have pre-created this documentation, so let us explain the documentation. Let t be the time domain of the model. Here t is defined as a half-open interval from 0 to infinity, excluded the infinity. And then let tile t, a subset of t, be the set of time indices in the dataset. So here tile t would refer to the value in the normalized year of our dataset. So it will be value between 0 and 1. Okay, for convenience, perhaps we need to display the TF norm. Okay, now suppose a map psi, which maps from the Cartesian product of the three-dimensional Euclidean space with the set T. It maps to the set of all real number R according to this notation, defined by psi sub vector x of t is equal to x sub naught times e raised to the power x sub 1 times t plus x sub 2 for every x sub naught, x sub 1, and x sub 2 in R, meaning that they are real numbers, and t in t. Now let epsilon, which maps from the set T to R, be the actual historical carbon emission of Indonesia, meaning that epsilon of T is the value in the column CO2. So it does not refer to the old dataset, it refers to the CO2 here, so it's this value in the dataset for every T in tile T. Now let capital psi, which maps from the three-dimensional Euclidean space to the half-open interval from 0 to infinity, excluding infinity, be an objective function defined by the following expression. If you observe this expression closely on the right-hand side, you would notice that this is the mean absolute error. Here we have a summation which sums the absolute value of epsilon of t minus psi subvector x of t. It is all summed over the tile t and then divided by the cardinality of tile t, which basically is the length of our dataset. So we have 273 rows, so the cardinality of tile t would be this number. And our model is a map epsilon hat from t to R, defined by epsilon hat of t equal to psi sub vector a of t, such that a, which is a three-dimensional vector, minimizes capital psi. So we can determine the vector a by making use of DAMSMEL. First we need to implement the psi function and the capital psi, which is the objective function, into Python. First the psi, which is defined as lambda, which maps x and t, defined by this x naught multiplies with npe, which is the Euler number in NumPy, raised to the power x1 times t plus x2, and then capital psi, so lambda, which maps x to the mean absolute error defined by this expression. Okay, we would use numpy min, then this code absolute value of the df norm CO2, which represents this epsilon t minus this numpy array, which represents psi sub x of t. So let us run the cell. Okay, now we proceed with instantiating DAMSMEL for optimization. Okay, first we define DAMSMEL as the DAMSMEL Python class. So here we have a few hyperparameters. The first is psi, which refers to the capital Psi function that we have defined earlier. Okay, so we put it there, and then we have dim, which refers to the dimension of the domain of the capital Psi. In our case, we have dim equal 3. Okay, now we define the solution as DAMSMEL optimize, and we have several hyperparameters here. The first is u, which is the initial starting point of the iteration. For simplicity, we would use an array of 3 values, all are 1, and then delta naught, which is the initial distance of adjacent points in the sample generated by DAMSMEL during the iteration. So we set it to be 10, and then we need to set alpha. By default here we set alpha to be 0.1. Alpha is the exponentially decaying rate of the distance in the process of the optimization by DAMSMEL. In our case, we would use alpha 0.01, and then S we set it to be 5, and T we set it to be 3, and then R, which is the threshold in which we want DAMSMEL to reset its adjacent distance to avoid getting stuck in local minima. So we set it to be 10 to the power of -5, and then the number of iterations to be 3000, and then we set the verbosity true. So during the iteration process, we will know the iteration time at each iteration. So let us run this code. Okay, the run is complete and it takes 105.7 seconds. Now let us observe the monitoring during the optimization process by DAMSMEL. So this is the tabular representation. We would love to plot this table for a better understanding. Let's set the color first. Okay, so this graph shows how DAMSMEL performs its optimization. So on the x-axis we have the number of iterations, and on the y-axis we have the loss function, or the number of loss at each iteration. So we see here initially the value is bigger, and then it getting smaller, and at some point around 1500, more than that perhaps. So this spike represents the way DAMSMEL tries to escape local minima, and then proceed the iteration, and it gets a very small value at 3000. Let us first reconstruct our module. Okay, we would use the inverse min-max function. So first on the df norm we set the prediction performed by DAMSMEL on the model on the head epsilon. So it will be psi of solution, which we got from DAMSMEL, comma t for t in df norm year. Now we would, okay, we forgot to name the columns model. We'll also give the same column model on our original dataset df by performing inverse min-max. Okay. Perhaps you want to emphasize the scale of the model would also be in metric tons. Now we want also to compute the coefficient of determination of our model. Okay, let us now plot the reconstructed model along with the original dataset. We would include the information of the coefficient of determination in the title. So let's visualize the reconstructed dataset. So here's the visualization, and our model fits very perfectly to the original dataset, as we can see on the graph. So this is the end of this tutorial. If you like the video, please like, and don't forget to subscribe Abstract. Thank you very much.